Hey, hi. Thanks for coming out here. So this talk is going to be about Orwell's 1984 and what we can learn from it about programming and how can we usefully apply it to our daily programming. In case you're wondering why are you listening to a talk about a book, it's because first of all I really like that book, and second of all this analogy between the book and programming is really fun, and I really enjoyed exploring it, and I'm hoping that you will enjoy hearing about it at least a little. So show hands, how many people here have read the book? A few. Okay, so don't worry, the rest of you. I'll just make a quick recap of the important points for this talk. The book describes a dystopian future where everything is under the control of the party. So the party controls everything, sees everything, and does everything. And the head of the party is one of the most iconic figures from the book. It's Big Brother, which sees everything and watching you constantly. And one of the methods of control over the population is through the language, which is called newspeak, which is specifically designed to make it hard to express thoughts freely and made to limit the range of thought. And here are some examples of newspeak concepts. So thought crime is the act of thinking something which is forbidden, and this crime is punishable. And one of the possible punishments is to become non-person, where you're being completely erased from history and from existence at all. And the last example, double plus and good, is how we can compose the language from smaller bits, thus making the language smaller and more modular, so to say. And to the main focus of the book, these are the party slogans. So war is peace, freedom is slavery, and ignorance is strength. And I'm sure it sounds kind of awful, but we'll see how we can map each and one of these slogans to something useful as we can learn about programming. So you can view it as sort of an outline of this talk. So we're going to go over the slogans one by one and just see how we can map it into something we can apply to software. So first, but a quick disclaimer. So this is just an analogy. Don't take it too seriously. Whatever I may say, you are not thought criminals. You can do whatever you want with your own code, but always be aware that Big Brother is watching, and so careful. Okay, so to our first slogan, war is peace. The examples, I'll start quite basic. Hopefully the first examples will be familiar to most of you, and I'll slowly pick up the pace, and I'm hoping that we'll have something interesting for various levels of knowledge. So, before we can talk about war, let's see what do I mean by peace. So I claim that this is peace. Now this code is scary, and it's here just to scare you off. And you don't actually have to read it at all, so I'll just hide it away. And the reason is that I call it peace is because it embraces a number of enemies and tries to live with them in peace. So specifically, we have side effects and mutability, which make reasoning about the code more difficult. We have nullability, which the handling of nulls obfuscates the flow of the code. We have exceptions, which make control flow even more complicated than it must be. And the last thing is multiplicity, which is when we try to handle some code multiple times, typically with a loop, and all the noise that we gain from doing that. So it again obfuscates the flow of the code and makes it harder to talk about it. And so, generally speaking, these things are called effects. So the things that make our code more difficult to reason about and read, write, and comprehend. And the code on the previous slide, as I said, embraces those effects. It just uses them freely all over the place and lives with them in peace. And the result is quite horrible code. So the point of the slogan now is that we're going to open a war against effects, and hopefully we will regain our real peace inside our code as a result of this war. So before we can actually go to war, we need to define some sort of a battlefield. And for this purpose, I'll use the TOE example, which I'll just use throughout this presentation. And it will be based on one of the recurring themes in the book, is that the idea that 2 plus 2 equals 5, and that the party can actually make you believe this fact. Now, we as programmers actually can make it a reality just by modeling it as a real program. So we start with a small arithmetic expression language. So we're supporting three actions: addition, multiplication, and plain numerical values. And we can evaluate expressions using a simple eval function. So we're going case by case over the possible actions and evaluate them accordingly. So addition goes to addition, multiplication, multiplication, constants to constants. And the main point here is that 2 plus 2 actually equals 5. And so we've managed to make the party reality into our own reality here. And we can use it as you might expect it to. So if we're constructing a small expression, we can evaluate it and create a value either 13 or 5 in the case of 2 plus 2. So this is the battlefield. Now we're ready to go to war. And so let's tackle our first enemy. So hopefully with this card, I don't actually have to convince you that side effects and mutability are actually a bad thing which you should avoid. So much so that ideally the language should make it difficult up to impossible to actually use them in the language. Like Scala and most other languages are actually not that good in limiting the scope of side effects, but I'm just going to pretend that side effects don't exist at all during this presentation. And so I'm just going to ignore this enemy and just vanquish it just by not thinking about it. And so we can move on to our next enemy and actually handle it properly. So the next one is nullability. So what does it mean that something is nullable? Is that the computation that produces this value may produce an empty value, a missing value. So like the ampersands in the book which are missing, so do values in the program can be missing as well. And since we're dealing with numbers, we're going to make a number disappear. So here's an example of a variation of the eval function that makes the number 7 disappear here. So instead of returning 7, we're returning null. And so the price that we're paying for this, the fact that we're using an effect here, is that everywhere where we're trying to work with the results of the eval function, we have to do null checks. So our code is less readable because we're peppering it with null checks. What's more important, even the fact that nulls are not checked at compile time. So the compiler doesn't actually know that we are dealing with nulls, and if we forget to do the null check at the appropriate location, we will end up with a runtime exception. And so this is not acceptable in production code. But nonetheless, this example works and produces the right value. So in case we're using 7, the result of the whole thing is null. But this is not far from ideal, and so we're going to, as the slogan says, open a war against nullability. And for this purpose, we actually need to understand what nullability means. So to actually understand the essence of some problem, one of the best ways to deal with it is to model the problem with a type. And so we'll have a dedicated type for nullable values. So a value of type A that can be missing will be nullable of A, and it will have 2 cases. So one is when the value is actually present, so just a wrapper around an A value, and one when the value is missing, and just a constant that replaces the missing case. And now we can rewrite our previous function from before using the nullable type. So instead of returning plain numbers, we're now returning nullable of these numbers. Now the code is still quite noisy. We're still doing lots of matches explicitly on our nullable values, but we do have a concrete advantage here. So the fact that we marked the function as nullable of int, now the compiler knows that we're dealing with nullable values and will enforce these checks at compile time. If we forget something, the compiler will complain and tell us we actually have to handle all nullable cases. And of course it works as before, but then instead of returning null, we're returning a missing value. In case the value is present, we actually have a wrapper around our value. Now, if we look at this pattern of pattern matching, we can kind of see the common theme here, and we can, like most programmers do, try to abstract it away with to avoid the repetition. So we can write a higher order function which will handle this pattern of pattern matching, and we'll do it like so. So we'll define once for all this pattern using, we'll call it chain nullable. So it takes a function from A to a nullable of B and tries to apply it to the current nullable value that we're working on. So we're pattern matching on this. And in case the value is present, we just apply the function. In case the value is missing, we're just propagating the missing constant. And so this takes care of pattern matching once and for all for us in the future. And so we can rewrite our example from before using the chain nullable function. So now it's much cleaner. So we're not repeating the pattern matching as before, we're just using chain nullable. And just as safe as before. So the compiler is enforcing the fact that we're treating nullable values as first-class things. But it's still far from ideal because there's nesting here. So the code is somewhat obfuscated by the fact that we're nesting calls to chain nullable, and it won't scale with lots of nullable values. So if you had more than 2 values, it will just keep on going to the right side, and it would probably be a nuisance to handle it. At this point, we can actually, if we squint hard enough, we can recognize one of the more common abstractions in the functional world, specifically the mount abstraction. And so this pattern of usage that we had here before is captured very well with the monad interface. And the core function of the monad interface is the flat map function. Which is, you can view it as a generalization of the chain nullable function, but that works with any f value that takes a type parameter, and we can read it as follows. So, given some f that some context f that wraps an a value, we can unwrap this value and pass it on to some function, produce an f of b, a value b in a context, and the whole result of this chaining becomes f of b. And so, having recognized that we are dealing with the monadic interface, we can recall that Scala has special syntactic support for the monad interface and flattened functions, specifically the for comprehension syntax. And we can rewrite the code from before as follows. So the rest of the code is the same, but here we're using the for syntax, also called monadic comprehensions. As you can see now, our code is straightforward. We no longer have any nesting. So the code, we can say, lives on the happy path. We're no longer looking at the missing case. We're just handling the present case. And the for syntax, which the sugars into flat maps, takes care of propagating the missing values for us as necessary. And so, having completely isolated the enemy behind the dedicated type and the monad abstraction, our code now is truly in peace. So we managed to actually regain nice properties of the code. And so, having dealt with this enemy, we can move on to our next one. And so, next enemy was exceptions. With experience with nullable types, we're going to skip ahead directly to defining a type that will capture the essence of the enemy that we're dealing with. And so, we're going to define a computation of type A that may fail with an error will be an exceptional value of type error and A. Again, we have two cases. One when the value is present and everything is okay, and the other one when the value is missing and we have an error of type error. So it's not a constant like in the previous case. And having seen how useful is the monad abstraction from before, we'll define flatmap straight away. So we're doing the obvious thing. We're just applying the function where applicable and propagating the error if it's not applicable. Now we can write another eval function like before. In this case, we're returning an exceptional value. And now the multiplication of values is forbidden. It's an error value. But notice how the core function here, the core functionality here is exactly the same as before. So the for syntax takes care of abstracting away the error propagation and does everything for us. And so again, we're living on the happy path while the type and the monad abstraction take care of doing all the hard work for us. And again, it works as you might expect it to work. And again, so with the same powerful abstraction, we managed to vanquish another enemy, and we can move on to another enemy while living in peace, in real peace in this piece of code. And so the last one is multiplicity. And so what does it mean to have multiplicity? It means that a single computation can produce multiple values, something that the hero of the book actually experiences, where 2 plus 2 can be multiple things at once. And so, again, we'll start by modeling it with an appropriate type. So what does it mean that a single computation can have multiple values? It means that we have a list of values. And so the list type models multiplicity appropriately. And since the list defines a flat map in the obvious way, we can skip ahead and just start using it. So let's code the example from the previous quote. So in this case, we're evaluating, but we're returning a list of numbers, and addition of 2 plus 2 yields 3 and 5. So we have two results simultaneously. And notice again, the core logic of this code didn't change at all. The same for syntax as before, nothing changed at all. It's just as readable as it was previously, but now we're dealing with a different effect. And if we actually run this code, we can see that the for syntax does all the heavy lifting for us by cross-referencing all possible computations coming from this 3 and 5 and produces a list of results for us. So doing all the cross-multiplication as appropriate. And so again, by being at war with the effect, we've managed to make our code remain in peace. And this actually concludes the war, so we can recap. So we should try and recognize our enemies in our code for what they are, effects, such as nullability and exceptions. We should look at their essence and try to represent them in a precise way, preferably some type. Along with the type, we should try and reduce the noise that we have from dealing with this special type by choosing an appropriate abstraction, so like the monad abstraction that we used previously, but there are many others. And once we've done all that, once we open the war against effect, our code can truly live in peace. And so indeed, war is peace. Okay, so to our next slogan. So freedom is slavery. So again, let's start again by illustrating what do I mean by freedom. So one day your boss is entering the room, and he tells you that the wonderful arithmetic library that we've just written is actually production ready. We can send it to our clients and let them use it as they desire. And so our clients are using this code. They're like writing serious expressions with this, like going all over the place with more and more complicated stuff, and like going completely insane. But one day, you see this expression. Can anyone see what's wrong with this expression? Probably not. So if we focus on the numbers, this should be more apparent, the specific problem with this expression. And specifically, this is obviously a subversive message against Big Brother in disguise. And your boss comes in, and he's not happy about it at all. And so this cannot pass without the appropriate punishment, and so the outcome is obvious. And now it's time to reflect what went wrong in this process, so we can turn back to our past and try to figure out what went wrong. And so it's actually quite easy to spot the problem. So if we recall the original definition of the expression language, we have three constructors here, and all of them, they're completely exposed. We gave our users full freedom to do whatever they like with them. And for the freedom that we gave them, we're now slaves of their choices, the choices of the users. So in this case, enslavement means that we can't verify correctness of the code using the library. And so it is possible to actually write code that is wrong under the definition of our domain, so like the example on the previous slide. And fixing this in this particular case is actually quite simple. We have to somehow reduce the freedom from our interface. So we have to constrain our users to use some subset of the functionality. And so this is Scala-specific syntax, which applies pretty much anywhere. But by marking the constructors as sealed abstract, we make it impossible to instantiate these case classes anywhere except the source file where they're defined. So now our users can't use our library at all, which is zero freedom in this case. But so, because we do want them to use the expressions in some capacity, we'll provide them what we call smart constructors. So we'll give them a way to construct expressions. So in this case, we're going to define an apply method on the add value, which takes the expression. But remembering that war is peace, instead of returning an expression, we're returning a nullable of expression. So in case the expression is not valid, we're going to return a missing value. Otherwise, we'll return the expression that the user tried to construct. And so this constructor is smart in the sense that it validates the input. And we can implement it quite simply. So we just pattern match on the values. In case of the wrong value from before, just returning a missing. But in case it's okay, we're just instantiating a new instance of the add value and returning that wrapped in a value constructor. And we can do the same thing for the other constructors, but we don't have any special validation, so we just always instantiate them just as before. And now to actually use these smart constructors is actually quite simple, since we still have the same for syntax as before, so we can just construct new values as appropriate. So in this case, we're constructing a valid value and it's okay, but in the wrong, when we're trying to construct the wrong value, we're getting a missing value because it doesn't pass the validation. So by limiting the freedom of the client code, we managed to make it impossible to write incorrect code. So we're no longer slaves to the user's choices, and we can be confident that all code produced by this library is actually correct. Though in general, actually finding out the right amount of freedom to give to our users is actually quite tricky, and it's not always a clear-cut choice. So to illustrate this point, let's try another example, which is slightly more interesting. So again, our boss comes in and tells us that what we're doing here is censorship, which is obviously great, so we should do it more of it. But instead of doing this primitive censorship, we'll try to do something more sophisticated. And so here are the new requirements that we get from our boss. So we're going to process expressions, this process can either fail with a message or succeed. And as censorship sometimes does, it can silently rewrite the input just because it feels like it. And so since we're used to using types all over the place and modeling problems with types, we're going to define a type specifically for this problem. And so here's our censor type. It takes an expression, which corresponds to processing an expression. It returns an exceptional value, which can fail with an error message or produce an expression as a result. And since this expression parameter is free to be anything, we can actually incorporate rewrites in here just as well. And so we can try and write a rule using the signature. So here's an example of a censor. It does a few things at once. So first of all, 4 silently turns into 5. 7 is still illegal. And we've added some constraints on the ability to do addition and multiplication. But since we're still in the mode of war is peace, we have the same core logic as before, the same 4 syntax, which allows us to do to write nicely the rest of the rule. And as the quote here says, it becomes quite difficult to do math this way, but nonetheless, we can try and run this code on an example. So here's the first value, which is okay. So we added 4 and 6, but 4 got rewritten into 5, which is expected. And in the second case, we've created a wrong value. So 7 is a non-person, and so the value 7 here made this whole process fail. But we actually have a problem here. Since apart from 7 being a non-person, we have another rule that forbids multiplication by 3 and another rule that forbids addition by 9. And so both of these are illegal, but we actually have only a single error message, which is somewhat deficient. Obviously, this should be expected because our type that we've chosen for this problem mandates exactly having 1 string as an error message. So we can't expect to have multiple strings as a result of this whole process. So this is obvious. But since the problem is with the type, we can try and fix the type to match the new requirements. So in this case, we'll define a new censor type, which instead of returning a single string, will return a list of strings, in which we would like to accumulate all the errors of the process. And so with the new type, we can rewrite our example from before. It's pretty similar to what we had previously, but now we're wrapping errors in the list constructor. And since we're already used to using for comprehensions and expected to actually magically take care of all the logic of propagating everything that's required for this to succeed, we expect this to actually handle the new list type in our constructor. And so we can try to run this rule again on the same example as before, but as you can see, we do have a list of strings, but a list of a single string. So the magic that we're used to is now not quite working out as we expected to. And then your boss comes in again, and he's saying that you're suppressing important ideological content, and that saddens him quite greatly because he worked so hard to formulate these messages. And of course, he won't be sad forever, so at some point, sadness becomes rage, and you'll get punished again. And so now that we are no longer existing, we can actually again reflect about the errors of our ways and try to figure out what was the mistake that led us down this path. So, heading back to the original censor type, since the whole thing started with modeling things with types, probably the problem is with the type. So if we recall the definition of the exceptional values, we used the monad interface to actually work with exceptional values. Now, if we look at the definition of the monad interface, we can see the problem just by reading the flat map signature. So if we think of f as some sort of action that produces a value, we can read the flat map in the following way. So suppose we have an action that produces a value of type A, and we can inspect the value of type A and choose the next action appropriately, and the result of the whole process will be an action that produces a value of type B. Now, in the case where we actually don't have an A value, when the action didn't produce a value, like the failing case in the exceptional type, then we won't have an A value to pass into the function here, and so we will never actually invoke the second action. So essentially, flatmap short circuits the computation for us. So if we look at it from another point of view, flatmap gives us a lot of freedom. Specifically, it gives us the freedom to choose the next action based on the results of the previous action. Now, if we look at our code from before, and this is the same code as on the previous slides, but with the 4 distributed into flat maps, we can see that the evaluation of the second rule is actually not dependent on the evaluation of the first rule. So we were given some freedom and we abused it. And now the price that we're paying, the enslavement that we gain for this freedom, is the fact that we cannot produce some useful information about our computation. We cannot accumulate errors. Now, since the problem is excessive freedom, the solution will be to somehow reduce the freedom of the interface and make it somehow more constrained in what it can provide us. So luckily there are many abstractions beside monad, so we can actually try and look for another abstraction which will be somehow more constrained for our purposes. And so we'll start with the most simple abstraction of them all, probably. So the functor abstraction abstracts over things that can be mapped over. So given an f of a, some value wrapped in a context of type a, and a function from a to b, we can produce an f of b. Now this is obviously much weaker than monad because we cannot implement flat map using map alone. But on the other hand, it's too weak for our purposes. You can't do much with functor, so we won't be able to actually solve our problem using functor alone. And so this is too little freedom for our purpose, and so we'll have to look for another abstraction to actually provide us with a solution. And so here's another one called Applicative. So it extends the functor abstraction with more methods, and the core method here, which we will use, is the function map2, which given two actions, f of a, f of b, can combine them into a single action f of c using a function that operates somehow on the contents of the actions. Now this is obviously stronger than functor because we can implement map using map2 and unit alone, but this is weaker than monad because we cannot implement flat map using map2 and unit. But what's crucial for our purposes here is the fact that map2 doesn't give us a lot of freedom. Specifically, we cannot choose f of b based on the results of f of a. They're completely independent. They're evaluated separately, and we can't choose one based on the other. So we have less freedom here. And this constraint, or lack of freedom, is what will actually allow us to accumulate errors the way we want to do. And so let's see how it works. So we'll define a new type just to not confuse it with the old exceptional value. So we have now a type censorship of A, which again has two values, one where the case is passing and the other where we have multiple errors, so a list of strings. And now previously we were defining the flatmap function to implement the monadic interface. Now we will actually want to avoid the monad interface because it's not constrained enough, and we'll implement applicative instead. So for this purpose, we'll need to implement map2. And so giving two values of censorship, so fa and fb, we're going to pattern match them and case by case do the right thing. So in case both of them are passing, we're just going to apply the function, the callback function that we've got here and pass it on. In case one of them is failing, we have no choice but to pass the errors onwards, just propagate them down the line. But in the last case, which is the crucial one, is in the case where we have errors on both sides. In this case, we have access to both of them, and we can combine them into a single list value and propagate a new failing value which has a list of all the errors from both sides. This is exactly error accumulation. It's what we wanted in the first place. So we can actually try to define a new type. So now censor is a function from expressions to a censorship of expressions. So we want to use a new interface to actually do the processing here. And we can rewrite the rule from before, using the new censor type. So it's quite similar to what we had previously. So the error cases are just wrapped in new constructors. But now, since we're no longer using monad, the monad interface, we don't have access to the for comprehension syntax or the flatmap function. We only have map2. But in this case, it's not that bad. We're still on the happy path. We don't have to handle failure. But what's important here is the fact that rule A and rule B are evaluated independently. So even if rule A failed, rule B will still run, and we'll still get access to the errors from rule B. And so we can actually apply this to the examples from before. So in the passing case, we have the same behavior as previously. We have a single passing value. But in the case where we have multiple failings, we have now a list of errors. So by limiting the freedom of the code, we managed to achieve our goal, in this case, extracting some useful information about the computation that we're performing. And so to conclude, when given freedom on one level, we're bound to pay for it on another level. We're enslaved to the consequences of this freedom, and this can be the risk of producing incorrect results, like in the first example, or the inability to extract some output from a computation, like in the second. And even more generally, limiting the freedom of code helps us reason about what it does, since the less it can do, the more we know about what it actually does. So of course, one cannot take away all of the freedom from the code, although it's tempting. And so since otherwise it will be completely unusable, like the example with the functor abstraction, which was too weak to actually implement our solution. So we can't take all freedom away, but we should give the bare minimum of freedom that we can and give exactly that and no more, since otherwise we'll again be enslaved to the consequences of this freedom. And once you start using mathematical abstractions like monad, applicative, functor, and many others that are available in the world of functional programming, freedom becomes something that can be quantified. And so choosing the right amount of freedom in our code becomes choosing going up and down the abstraction ladder. So we can choose the right abstraction, and we can quantify how much freedom it gives us just by inspecting the properties of this abstraction, which is a great benefit when trying to reason about how much freedom to give some interface. And so this concludes this slogan. So now we're ready for our last slogan, ignorance is strength. So for this part, I'm going to assume that we're not going to use any of these things and features of the Scala language, which is not such a great loss since typically they're just dangerous or annoying or both. And so we're just going to pretend that they don't exist in the language at all. So the question is, what can ignorance actually bias? So here's an example. Can anyone guess what this function does? Almost. Okay, so I lied in the name of the function. It doesn't add to. Now, obviously, names of functions that don't imply anything and don't guarantee anything at all, but the problem goes much deeper. Since the fact that the function operates in integers, the function implementation has access to all possible functions that integers support. And so the implementation of this function is completely unconstrained. So as we know that freedom is slavery, this is lots of freedom to do whatever you want, and so we can't say anything about this implementation. Our question is, what happens if we raise the specific knowledge about this function, become ignorant of our inputs, and so we can create a parametric function. So for any a, given an a, produce an a. Can anyone guess what this does? Yep. So the only implementation, given the previous slide, for this function is the identity function, and the reason for it is because now a is a type parameter, so it can be anything, and consequently we don't know anything about it. It has no functions that we can actually operate on it, and so we can produce a out of nothing because again we don't know what value it is. And so since the only a in scope is the a that we got as an argument, we have to produce a as a result. So this property of code that makes reasoning about parametric functions more approachable is called parametricity. And phrased into this use case, it means that the less we know about our inputs, the more our outputs are constrained. So from ignorance, we manage to gain some strength. Now, of course, not all functions can be determined uniquely like the identity functions. Some functions are actually slightly more complicated than this, I think. But nonetheless, the point still stands. Parametric functions are easier to reason about just because they're more ignorant of their inputs. Now, let's not only that we can actually reason about the functions, parametric functions, we can actually use the compiler to help us catch bugs in parametric functions as well. So here's another example. So we have a swap function, which takes a tuple of numbers, and presumably, using its name, was supposed to swap the two integers in the tuple, but I made a bug, and it actually doesn't do it at all. And so this is a runtime bug. We'll catch it in production sometimes later during the night, and something bad will happen. Now, if we actually take the knowledge about this function and then erase completely the specifics about what we're dealing with, so we remove the knowledge about integers and convert it into a parametric function with a and b as type parameters, we now can actually read the signature of this function. Tuple a b becomes a tuple b a, and just from reading this signature, we can deduce what it does. It has to swap the two inputs. But apart from us knowing what it does, more importantly, the compiler knows what this function does now. Because now this bug is a compilation error. And so the compiler will actually catch problems for us. Now, both of these examples are quite simplistic, and so I would like to have something more complicated just to illustrate the point about ignorance. And so we'll try to do it quickly. So, as sometimes happens in big organizations, while we were working on our wonderful arithmetic library, someone else was doing exactly the same thing. And they came up with their own solution, which is quite similar to ours, but slightly different. So now we have expression 2, which instead of having separate operations from addition multiplication, has a single constructor that takes an operation as an argument. So this is quite similar to what we had, but slightly different. And it will be a shame to copy the important business logic that we implemented for our previous expression language. So we'd like to have some reuse. And it's actually quite simple to convert between the two expressions, and so expression types, and we can write a conversion function that translates between expressions of the second kind into the expressions of the first kind. And so this is a straightforward recursive function. So we are given some expression of the second kind. We take a single layer of it, convert it into expressions of the first kind, and recursively convert its parts. And now if we try to convert an expression of the second kind, we get the expected result. And if you want to actually apply the eval function that works on expressions of the first kind to the new expressions, we can just compose the two functions together. So if we give an expression of the second kind, we first translate it into expressions of the second kind, and then evaluate it using the old function that we had before. And this does exactly what you might expect. But then, as always happens, our boss comes in yet again. And annoyingly, it tells us that our clients are going completely insane with our expression language and are writing huge, huge trees. And our eval function that works on expressions of the second kind is actually quite inefficient. It takes 2 passes to actually convert the tree into a number. So first it translates the whole tree, builds a new one, and then evaluates the resulting tree. So it's 2 passes over the same tree, and it's quite inefficient. And Big Brother actually cares about performance quite a bit. And so what can we do? How can we make it somehow more efficient? If we look at the definition of our original eval function, we can actually see the problem right in the definition. So this function does 2 things. First, it evaluates stuff, so addition, multiplication, or just values, but also it recurses on the input. And so this recursion is traversing of the actual tree. So we mixed the evaluation logic together with traversal of the tree. And so if you could somehow separate the traversal of the tree from the evaluation logic, maybe we would be able to fuse this function with the translation function. But this pattern of recursion is actually quite common, and we can see another example just to illustrate the point. So here's another function that sort of evaluates expressions. So it's the print function that produces a string from an expression. And we can actually summarize the pattern as follows. It becomes quite apparent with two examples. So given some value of some type A, so it can be int or string, what we're doing is recursively convert our expressions into instances of A, and then we combine the resulting A's into a single A and propagate it onwards. So we have 2 parts here: the conversion and the combination of A values. Now the actual traversal of the tree, the recursive part here is actually common between the 2 functions, but the combination of the values, the A values, be it strings or ints, is actually what unique to each function here. So if you could somehow abstract away this pattern, maybe we'll be able to fuse something. We could do something similar to what we had with chain nullable, but it's actually it's solvable. But actually, the problem goes even deeper than the specific functions that we're using here. And if you look at our original expression language, we can see the problem starting right there. So specifically, expression is a recursive data type. So what does it mean that it's recursive? Is the fact that its own definition uses expression in the definition, and we can see that the recursive calls to the expression type happen exactly at the same spots where we have the recursive calls in our functions. So if we could make our type somehow more ignorant of its recursive nature, maybe we'll be able to somehow separate away the logic of combination from the logic of traversal. And so we'll do exactly that, and since we're used to working with types, we'll just use yet another type. And so expression step of A stands for a computation over expression values that produces a value of type A, be it int or string. And so we have cases for each of the constructors from before, but notice how the recursive calls from before are now type parameters. So we managed to erase the knowledge about the recursive nature of this data type from our definition. And now we can try to rewrite. So if we actually look at what the meaning, what does it mean to have an addition step? It means that we have 2 values of type A that someone already evaluated, and now we have to find a way to combine them in the addition step. And so we can try to rewrite our eval function from before using expression step. And so we can say read the add step branch as follows. So suppose someone already computed and converted A and B into numbers. What will we do with them? Well, we'll combine them into combine them using addition and produce a new number. Now the next step will be taken care of by someone else, not us. And so this function is exactly the logic from before, but without the recursion. So we managed to separate the logic of combination of values from traversal of the tree. We can do the same treatment for the expression step for the translation function, rephrase it using expression step. So here we're peeling off a single layer of an expression, convert it into a step, and then pass on the parts to the next evaluation step, not for us. And so can we now fuse the 2 functions together? So ideally, we'd like to define something like this that takes a function that translates, a function that evaluates, and given an expression of the second type, produce a number. Now this is quite specific to the problem that we're solving. So let's, since we're trying to prove that ignorance is strength, let's try to erase some of the knowledge about the specifics of the problem. So we can remove the type arguments here and make them generic. So now we're working with generic functions. So given a function that unwraps A's into expression steps of A and a function that reduces expression steps of B into B, provided an A value, produce a B value. This is still quite specific to our problem domain. So can we make it even more generic, even more ignorant? So can we work on a generic context F and just work with it? So given something that unfolds A's into F of A's and reduces F of B's into B's, given an A, produce a B. And the answer is no, we can't do this, because in this case we're slightly too ignorant. We can't actually do anything with the f value, so it's a generic container type which we know nothing about, so we can't operate on it. And so we need to have some sort of interface to actually do something with this value. And luckily we actually know such a very simple interface that gives us exactly that. This is the functor interface from before. It lets us map a function over a generic container. And with this in hand, we can rewrite the final iteration of the fuse function, which reads as follows. Given a container type f that implements the functor interface and something that unrolls a's into f of a's and reduces f of b's into b's, given an a, produce a b. Now this is as ignorant as we can be. We removed any unessential information about this function as we could. And now the benefit of working with such an abstract level is the fact that we can derive the solution of this function, the solution space for this function is actually quite constrained. So we can derive the solution just by following the types. And that's exactly what we'll do. So we have now an a value. We have to do something with the a value. And so we have a single consumer for a values. It's from a. So we'll just apply from a and produce an f of a. Now we don't actually have any consumers for f of a, so we're kind of stuck, but we now can recall that f of a implements functor, and so we can, if we could somehow map a function from a to b, we could produce an f of b. And luckily we do have such a function, so if you partially apply fuse to the first two arguments, it's exactly a function from a to b. It takes an a, produces a b. And now we can apply map this function over f of a, produce an f of b, and now we have a single consumer for f of b, it's the to b function, produces a b, and this is exactly the result that we wanted to achieve. And so just by following the types, being completely ignorant of the actual problem domain, we managed to achieve what I claim to be an actual solution to this problem, and it actually is a solution to this problem. And just to be able to use it, we have to define a map function for expression step, but it's quite straightforward, and I'll just skip it ahead. But if we create an expression of the second kind, take the translation function and the evaluation function, fuse them together, we get the right result. And the fact that we could achieve this just by going abstractly, using abstract types, not knowing anything about the problem domain, still blows my mind till this day. If you actually don't believe me that it achieves the right goal, you can see a trace of execution, which I'll just run through because we don't have any time. But you can see that this tree is being reduced. On the way down, it's being translated, and on the way up, it's being reduced into numbers. So eventually, we'll have, by single passing over the whole tree up and down, we'll have the right solution. So to conclude, we should try and purge as much knowledge from our code as possible, because not knowing the context in which it is running, it restricts what it can do. And since it cannot use any specific details about its input to determine the result, we can use this ignorance to our advantage. So be it by determining some aspect of the implementation, or by allowing the compiler to help us construct the code for us. So indeed, ignorance is strength. Sorry. I find this quote quite fitting to everything programming. To sum up, these are the three slogans. So we saw how we can connect each and one of them to some idea about programming. If you take anything away from this talk, is just print this out, put it in your office, and just let people live by these slogans. Hopefully it will help them write nicer code. And so we saw that war on effects brings peace to our code. Freedom on one level is slavery on another. And ignorance can be leveraged to help us write code as well as reason about it. And just quickly, some resources. So each section, the whole code and the presentation is available here, and each part has some resources. I'll just say that the fuse function is an instance of something more generic called recursion schemes, which is a big topic, and the fuse function is just one building block from it. And the way to learn about it is either this academic article, which is not quite accessible, or this blog post series, which is more accessible. I think that concludes our talk.